Okay, I guess we can start. So, welcome to lecture 4 of our course on federated learning. I would like to begin with a quick uh, orientation within the course. So, by the end of today, we have completed half of the lectures. As I mentioned in the beginning of the course, we will have a relatively dense March with 8 lectures and 8 assignments, which is a sort of a boot camp where you learn the core tools and techniques. And then the second half of the course in April and May will be devoted to the project. And I have been just asked, is there project group work or individual? And the group work is individual work. So every one of you has to do a separate individual project. What else? Yeah, I have been asked about assignment 2, and I would like to also share the question and my answer with you here. So the question was about the update step in this federated learning algorithm. So in equation 3 here, should the W here be W superscript I? And it doesn't matter. So this W here is just the optimization variable. It's like a dummy variable in programming terms. So you just use this variable to formulate this optimization problem. What this optimization problem does, it's defining an update. So at time step t, you compute at each node I, you compute a new model parameter. This new model parameter is W superscript I, comma t plus 1. Yeah, it's a bit notation heavy, but I guess there's no way around it. And this new updated model parameter at node I replaces the previous one, which was W superscript I, comma t. Okay. Each node implements this update by solving this optimization problem. And then another question was, how should you solve this optimization problem? Can you do it with some gradient step? And here you should try to solve it exactly or up to numerical accuracy. You should try to solve this optimization problem. And the core idea of this assignment is to show or to point you to reformulating optimization problems as simpler ones for which you have solvers. So for which kind of optimization problems do you have solvers ready available in Python? Yeah, anything that is implemented in scikit-learn, like scikit-learn.fit functions. And you should try to reformulate this regularized training problem as a .fit problem. And it turns out you can do that by interpreting this second term here, this alpha times this sum over neighbors, as additional data points that you augment to your data set. So you can augment your local data set such that when you do linear least squares on this augmented data set, you solve the same problem as this regularized optimization problem. This is related to this equivalence, essential equivalence of data augmentation and penalty terms for regularization. These are just different ways to implement the same thing. Any further questions regarding assignment 2? You can also post them on the Zoom chat or ask them. You should be able to speak to unmute your microphone in Zoom. Okay, if there are no questions, then I would like now also to take this opportunity to take a little poll. So I want to ask you about the workload so far. As I said, it's quite fast-paced, the beginning. I just want to hear from you now. And those in the lecture hall, please raise your hand. So for who of you is the workload higher than expected? For who of you is it lower than expected? For whom of you is it exactly right? So, okay, I don't know any other option to ask, but I don't see many frustrated and super stressed people here. So, is the workload reasonable so far? It seems yes. A few say too much. Nobody says too little. Yeah, I guess that's natural. I would be very surprised. Although sometimes I get the feedback, I want to do more. Okay. Yeah, it seems we have a good amount of workload here. Yes, so let's now continue with the lecture today, which is a continuation of the previous one on federated learning algorithms. And today I will talk about federated learning algorithms that can also handle asynchronous operation. And this is the typical operation mode or type of computation we use in federated learning systems. We make a full screen here. Okay, are there any questions regarding the last lecture three, the previous lecture 3 on algorithms? So if not, I will quickly set again the stage. So I try to show you this, or I show you this slide in every lecture that I give. This is really the core mathematical structure of this course. It's a federated learning network. So federated learning network consists of a graph, an undirected weighted graph with the nodes being the devices. A device can be this here, can be this laptop, can be a smartphone, can be this desktop, can be sometimes light bulbs have a bit of computational power, or a small embedded system. Basically anything that can compute, so can train a model and communicate with other devices. So this notion of device is very generic, very abstract in this course. And some of these nodes are connected by edges, and the edges, they have weights. So this represents the strength of collaboration. So those devices that are connected by an edge, they collaborate or they couple the model training. And this is a design choice. So within this course, we assume somebody did the effort and told us the network structure. In practice, it might be difficult to find out the network structure because the federated learning network or the federated learning system might be a peer-to-peer network that consists of smartphones that are connected via short-range wireless communication, like Bluetooth. So you rarely know exactly the network structure. This is something like in epidemics when you have these contact networks. So this was a hard problem, or is a hard problem to find out if two people are near each other so they can infect each other. And you need to know this when you want to know the network structure for such a federated learning system. So this is a very large simplification, having or writing down a federated learning network. This is just a modeling assumption, a first guess, so to say. In practice, it's very difficult to know exactly the federated learning network structure. Maybe we have just very rough parameters about the network, like we know on average each device has 3 neighbors or 5 neighbors. That's all we can find out about the network structure. But here in this course, we start easy and we say we have it here on the slide, or you know it exactly as in the assignments. Okay, and beside the graph, each node or each device trains a machine learning model. So we have on top of the nodes, we have machine learning problems or machine learning tasks. So you can look at this also as a network of machine learning tasks. Each device, each one who has a smartphone has its own machine learning task, which is give me the best work plan for tomorrow to help me with my back pain, or to give me a back pain relief, or tell me the best diet to keep me healthy as long as possible. And these machine learning tasks are different in general. So old-fashioned medicine, or I don't know, maybe old-fashioned was not like this, but school medicine often uses averages. So we have one machine learning task, which is to predict optimal diet for everybody. But nowadays, the modern machine learning approach or the federated learning approaches, we have a separate problem for each one of us, a tailored, personalized model. And we model this, or we represent this by model parameters that we assign to each node in the federated learning network, and the usefulness of model parameters or a model is measured by some loss function. And this loss function might be different between different nodes might use different loss functions. For example, some of us might have access to a physiotherapy knowledge, so they know exactly what is the right activity for back pain. So they can use something like a squared error loss or some supervised loss function. Yet others don't have this knowledge. So I, for example, I have no training in physiotherapy or physical or sports medicine, so I can only guess. But I know, I feel it when it doesn't do me good. So I have another loss function, which is based on a reward signal. So this is more related to reinforcement learning. So this formulation is very, very flexible. We can couple machine learning tasks that are reinforcement learning problems with other machine learning tasks that are linear regression problems. And yet a third task in the network could be a clustering problem, so an unsupervised learning task. So I just want to really highlight the flexibility of this model that we use in this course. And actually in the next lecture, next Monday, you will hear about federated clustering methods, where the nodes, they don't have a weight vector or they don't use this linear model anymore, but they have a k-means model. Any questions at this point? No. Okay, and just to remind, we set then up federated learning as an optimization problem. So we want to train the model parameters, or we want to learn model parameters that have on the one hand a small loss for each node. So I might have a small test set where I can evaluate the model and then measure a loss. But this test set is too small in general. That's why we need to collaborate, and we enforce this collaboration by adding a penalty term or a regularization term, which measures the discrepancy between connected nodes. So far, so good. And then how do we get federated learning algorithms? And this is this basic workflow, a blueprint in the whole course. So we start from formulating your federated learning application as a GTVMin instance, and this you also have to do in your projects. And then you must come up with characterizations for the solutions. So the most natural way to characterize the solution of an optimization problem is, does anyone have a favorite characterization method? How do you characterize the solution of an optimization problem? Well, you write argmin, objective function, haha. Then you have characterized it. But if the objective function is a smooth and a smooth and convex function, there's a widely used characterization that most of us, I guess every one of us, learns in high school. How do you find the minimum of a smooth curve? You set the derivative to zero, so zero gradient condition. And this is just one example, and maybe the most famous example of a fixed point characterization. So you find some operator that I denote here by calligraphic F, which here looks a bit different, but this is just another example of an operator, different from the gradient step. Yeah, there was also the hint or the intuition of the gradient, and you just come up with an operator such that any solution of GTVMin must be a fixed point of this operator. And there are different choices for this operator. So you have some design freedom. Here is a design freedom. You can use the zero gradient condition, but you don't need to. You can also use another operator to characterize the minimum of a smooth objective function. But as soon as you have such an operator, and you can show that this operator has nice properties, that is, it's a contraction, you basically have immediately a federated learning algorithm at your hand, which is just iterate, repeatedly apply this operator. This operator F gives you the update rules that you need to do in each iteration, in each new clock cycle of the federated learning algorithm that runs in your smartphone. You must implement this operator F, or you must apply this operator f, which will involve some computations. Okay, so for GTVMin instances where the objective function is a smooth convex function, and this involves two things. So I want to remind you again that in this GTVMin problem, you have local loss functions, and they can be very different, and you have this discrepancy measure. So both need to be nice, that the whole problem becomes a smooth convex optimization problem. And if this is a smooth convex optimization problem, then you can formulate the optimality condition via this zero gradient condition, or you get one optimality condition like this. And it seems a bit strange why to rewrite this as this fixed point equation, but I want to, let's say, I want to sell this idea or this basic principle of solving problems by fixed point iterations. So I want you to learn to appreciate this in this course, in particular for federated learning, but this can be used in other cases as well, or in other applications. But in federated learning, it's particularly nice because we will see that these properties of this operator, of this fixed point operator, they directly translate into convergence properties or robustness properties of federated learning algorithms and systems that implement these algorithms. Okay, and yeah, how do you think can we characterize the properties of this operator? So these properties of the operator, of course, linked to the properties of the objective function f here. And what can we say about this relation? Which properties of this objective function f guarantee that this operator here, this gradient step operator, so I call it a gradient step operator, is a contraction, for example? Yes. Convexity, yes. So if f is convex and differentiable, otherwise we couldn't compute the gradient. Is this enough? So is convexity and differentiability enough that the gradient step here, which by the way depends on some parameter eta, which we call step size or learning rate, is always a contraction? In general, not. It's not enough. We need f not only to be smooth and convex, so like this, but we also need to somehow bound the speed with which the slope can rise. And this is related to smoothness. So a smooth function in the context of convex optimization problems is such that the gradient cannot change too quickly. Because if you have no bound on this rate of change of the gradient, basically the gradient step can always be made arbitrarily large by picking a very bad or very rapidly increasing function. So we need this. So we have here a gradient at point W2, and here a gradient at point W1, and these gradients, or the difference of these gradients, must be bounded somehow. Must be bounded by a constant beta times the difference of the arguments. So this is called beta smoothness. Did you hear the notion of beta smoothness before this course somewhere? No. Okay, so believe it or not, but just convexity and smooth differentiability is not enough. We also need smoothness. And what about this eta? How do we need to choose eta such that this gradient step is contraction? Do we have to choose eta very large? So when we take the gradient here and we make a very large gradient step, no, it doesn't work. So if this is the optimum here, if we want these gradient steps to converge towards the optimum, this eta needs to be sufficiently small. Okay. There any comments on the chat? No. What else? Do you think that it's now enough? So assume we have an objective function that is convex, smooth, so the gradient doesn't change too much, and we have found the right value for eta. So we can we guarantee that this gradient step is a contraction? Anybody on Zoom? Does anybody have a comment? Is the gradient step, can the gradient step become a contraction for a smooth, convex objective function when we choose the learning rate sufficiently small? Or might there be very bad functions that are smooth and convex, but which make the gradient step operator fail to be a contraction? Yeah, there's a comment, depends on the step size. So let's assume we choose the best possible step size. So we optimize the step size as much as possible. But is there a function f that is smooth and convex for which there is no choice for the step size eta, such that this gradient step becomes a contraction? Let's see. Well, it turns out there is. And this bad function is one which gets flatter and flatter. So like an exponential function which has no lower bound on the curvature. So we need a lower bound on the curvature. And this is called a strongly convex function. So we need to rule out such arbitrarily flat tails. And for this, to rule this out, we need to assume that the function is strongly convex. So only for strongly convex and smooth functions, we can find a step size such that this gradient step operator becomes a contraction. Yes, so if you use a proximal operator, I mean, this is another choice. So one choice for this operator results in a gradient step, and another choice results in a proximal step. But let's stick to this gradient step a bit more. So I really want to emphasize how the properties of this objective function translate into contraction properties of the operator. And you have, to some degree, you can control the properties of the objective function f, because this objective function f is this objective function of GTVMin. So it consists of these local loss functions and the variation measure. So how can you ensure that or guarantee that the resulting objective function is strongly convex? Well, you could, for example, choose the loss function, the local loss functions, such that they are always strongly convex, because then you add strongly convex functions with a convex function is again strongly convex. And one way to make a loss or a training error, so these local loss functions, they are kind of training error, to make this a strongly convex function is to add a regularization term, to add a term like plus lambda times local model parameters, Euclidean norm squared. This is sometimes called a ridge term, related to ridge regression. So if you add such a regularizer to the local loss function or to the training error, you make sure that this local loss becomes strongly convex. And this you can do. You can how can you add the square of the Euclidean norm of the model parameters to the training error? You can do it in PyTorch. Who of you uses PyTorch? So in PyTorch, you have pretty much control over the loss function you want to use to train a machine learning model. But what if you don't have PyTorch? Well, you can add such a term also by data augmentation, by adding synthetic or ghost data points to your local data set and then run whatever training algorithm you want to use, like in scikit-learn a .fit function for decision trees. Okay. Yeah, if we work out this gradient step for a particular choice of local loss function and a particular choice for model, let's say we want to train a linear model and we use the squared error loss. Okay, now let's stick to smooth convex loss function still. And write down this gradient step, we end up with two components in the gradient step, which have a nice interpretation. So in this gradient step, we have the gradient of the local loss, which means you want to, in this update, you want to pull or you want to steer the current local model parameters to the minimum of the local loss. Now, this makes sense. But then you have a counteracting term which wants to steer or pull the local model parameters to agree with the neighbors. So if the neighbors are very different, your update pulls the local model parameter away from the minimum, actually. And this looks somewhat, or this is somewhat similar to an ensemble method, where you also take into account you not only take into account your local model, but also the neighbor model parameters. So your local model parameter averages the current its current own value with those of the neighbors. Yeah, and this the relative importance of these two effects is controlled or steered by alpha times the edge weights. So when you have larger edge weights, the update puts more emphasis on the corresponding neighbor. So the update puts more emphasis on the neighbors that are connected by a large edge weight to the node I that we now look at. And you can also modulate the edge weights globally, all edge weights together by alpha. So if you choose alpha very large, you put all the emphasis on agreement with the neighbors, which means the solution, if this converges, if this ends up to converge, it must be such that all the local model parameters perfectly agree with the neighbors. That is, the solution is constant over all nodes. So if the solution is characterized by each node must have identical model parameters with its neighbors, does this mean that all nodes in the federated learning network have identical model parameters? This is what we can ensure by alpha. So if we turn up alpha more and more, we make alpha larger and larger, then this update tells us that if there is a limit to this update, so if this update converges at some point, it must be such that at each node, the model parameters are identical to the neighbor model parameters. But of course, there can be different components in the federated learning system. So the solution or the limit of this is constant over all connected components of a federated learning network. So in this case, in this simple example, the federated learning network is connected. So here, agreement with neighbors implies that all nodes have the same model parameters. But there might be other federated learning networks where there's no connection here. And then you end up with islands, so to say, in your federated learning network. Okay. So I have now written down this gradient step as an update rule, and naively implemented, or if we want to implement this in hardware, like in these devices, in smartphones, it seems a bit trivial, but it's actually very hard in practice to ensure that this update here that is shown here is executed synchronously. So in lock, each node has to complete this update, get its new model parameter at t+1 before it starts a new iteration. This sounds trivial, but if you for example simulate this update, this node-wise updates in a computer, and you are unlucky because you don't have a parallel computer where you really in hardware have one computing device or computing node for each node, you have to do it sequentially. So you have to iterate sequentially over the nodes. And then it might be convenient, as soon as you get an update, you override your local model parameters. And this means in a later node, you use already updated model parameters of the others, which you are not allowed to do. You need to use, on the right-hand side, you need to use the old or the current model parameters for all nodes. So there's a comment here: if alpha tends to infinity, then we force all models to be identical, but less importance to loss. So the global model would perform worse and worse. Very good comment. Yeah, this depends on the application. If in your application, if in a given federated learning application, you want to train one model based on different local data sets, then this is the way to go. Then you want to enforce the same model for each node. But this might not be the optimal strategy. Yes. In some applications, you might want to adaptively learn different models for different subnetworks of your federated learning system. But by the way, the standard server-based federated learning model uses exactly this. So it averages all the contributions from all clients. So in basic server-based federated learning, as you hear in the context of federated averaging, for example, you average all the gradients over all clients to train one single model, and this might not be the best way. So we have some more design freedom here by choosing alpha, some intermediate value for alpha, such that the resulting models at well-connected nodes are approximately identical. So I indicate this here by the colors. So the red nodes end up with approximately the same model, but this might be different from the models at the blue nodes, which in turn have their cluster-wise model. And we will talk more about this, and I will sketch some analysis. So I will try to develop some mathematical tools to characterize how large this alpha has to be such that this works in lecture 7, actually. Okay, yeah. So if we want to implement this in a real network, so we don't want to simulate, maybe we don't want only to simulate this federated learning algorithm like you do in the assignments, but in practice, you want to develop an app, a federated learning app that is installed at billions of smartphones, so to say. So how do you implement this algorithm there? Well, you need to do some form of message passing. You need to pass on your current model parameters to the neighbors you have, and this might be, for example, only one. The only one with a or the smartphone that is just in your Bluetooth range. You do this, you exchange this or share these model parameters in one time step, and then after you have exchanged it, you execute the local update. So you solve this optimization problem that I showed you before to get the new model parameters, and these are then shared to prepare for the next model update. And this is a very, very ordered process. So there's a very strict order of model parameter sharing and model parameter updates. And maintaining order is difficult in such a, think of a large federated learning system. As I said, you maybe want to develop a personal healthcare assistant, which is a perfect example for a federated learning application. And each node is a user of your app. So of course, you want to have 8 billion users of your app, everybody on the planet. And to synchronize this system is impossible. It's a nightmare. How could you synchronize this? Some people are awake, others are sleeping. We have different time zones. So this is a this is a mathematical abstraction. This is a fantasy land, which is nice for analysis to get some idea, some intuition how a system works, but this is often far away from reality. Okay. Yeah, so one way to implement this synchronization could be to have a central authority, like a clock, a global clock. Those who control the watch, they have a lot of power in federated learning systems. So you could use some server that helps you with implementing, which tells the clients, we are not there yet. So some of you still need to exchange your parameters. And as soon as everybody got the parameters from the neighbors, the server, who has a bird's eye view about the system, then tells everybody, now you can do your local update. And you can find a small Python demo that starts different instances of a terminal on your computer, linked here with this QR code. Okay, so the first variant of this basic federated gradient descent is called federated stochastic gradient descent. And the idea is, like in basic gradient descent, to replace the computation of or to replace the exact gradient with an approximation of the gradient, or a noisy approximation of the gradient. So what do? We instead of using the full local data set that is shown here, so the node I has mi data points, each with a feature vector and a label, so you can compute the gradient using the formula shown here. What could be the problem? Well, the problem could be this mi is very large. Large is relative. So it can be, if you have 1,000 data points, it can be already large for a small computer, like a Raspberry Pi system. So you want to reduce the computational complexity. How do you reduce the complexity of a sum? You use a smaller number of components in the sum. So you randomly select a subset or a batch. Yeah. Yeah. Yes, it's the same. Yeah. Yeah. Yes. So this very good comment. If we choose alpha very large in GTVMin, and the federated learning network is connected, this is essentially the same as training a single model from all the data together, pull the data together. But the advantage is we do it in a distributed fashion. Yeah. And this is actually a nice bridge to the next algorithm that I want to introduce, and then maybe is the most famous federated learning algorithm, which is called federated averaging. And in federated averaging, we say we want to have the same model parameters at all clients right from the start. So we want to basically learn or train a single model. Training a single model is the same as training or as copying the model parameters at all nodes. And this is what we enforce here in this optimization problem. So we want to minimize the sum of all loss functions subject to all the local model parameters are identical. So this is basically a stupid way or a nonsense way to rewrite a simple machine learning problem where you minimize the sum of all loss functions of the same model parameter. But it can be useful to rewrite it like this because it lends to using distributed algorithms. And these distributed algorithms, they don't force us or they don't require us to pool the local data sets together. So we can implement then the resulting training algorithm as message passing. And it turns out there's one nice way to represent this federated averaging as a projected gradient descent. So you could represent this equality constraints as a constraint set. So the set of all collections of local model parameters such that they're all identical. This is an affine, I think it's an affine set actually. So it's a convex set. And then you can ensure this constraint by projecting on the constraint set. First, you do a normal gradient step. So a gradient step in terms of each local model parameter. Each local model parameter does its own gradient step. So this is the local update. And then you combine those by a projection step. And the projection step, as you can show, is to compute the average. And that's federated averaging. So in each time step or in each iteration, you start with sharing the current model parameters to all nodes or all devices. And each device implements now a gradient step. So you do a gradient step on the GTVMin objective. But now you have this constraints. So you must take these constraints into account by a projection step. And the projection is exactly the aggregation. So you compute the average of all the local model parameters that you get from the local gradient step. So it turns out federated averaging, or a very close variant to what is known in the literature as federated averaging, is nothing but projected gradient descent on a GTVMin problem. Yeah, in the literature, federated averaging, the name federated averaging is used for a variation where you use stochastic approximations of the gradient. So you don't use the exact gradient as shown here, but a stochastic approximation based on a batch. And it's often useful to not only use one single gradient step, but several gradient steps. Okay. Why do you think it could be useful to do several gradient steps? Well, I want to remind you again that also this federated learning algorithm is an instance of a fixed point iteration. But it's maybe not so obvious what the operator f is here. So this might be actually a nice exercise for one of the next assignments. So identify this operator calligraphic f for this variant or basic variant of federated averaging. And if you not, and then you can say, well, maybe there's a better operator. In the end, you want to find an operator that has maximum possible contraction properties. Maximum possible contraction properties means contraction factor 0. So after one iteration, you are at the optimum. That's, of course, too much to ask for, but you could try, if I have a given algorithm like this here, could I tweak a bit this operator? Could I bend it a bit, massage it a bit, such that the new operator has a better contraction rate, a smaller contraction rate, so it converges faster? This also works, by the way, for basic gradient descent. It turns out you can modify a bit gradient descent to get another gradient method that uses a bit of a different operator that is different from the gradient step. And the resulting algorithms are much faster, converge much faster. They are called accelerated gradient methods. And similar here, you can you can find settings where applying not one single gradient step, but several ones, this corresponds then to a new operator, has a smaller contraction factor, so it converges faster. Okay, I've shown here, I'll show also here the canonical reference who is attributed to coining this term federated averaging and to coining the or to introducing the whole field of, or branding the field of federated learning. There's a comment. Reduce the communication. Yeah, if it converges faster, that's a good point. So why would you like to have an operator, a fixed point operator that results in faster convergence? Well, you need less iterations to achieve a certain accuracy, so less compute, but each iteration also involves communication. Here you need to broadcast from the server to all clients, and then you need to send back from the clients to the server. And if you have billions of clients, this means a lot of communication. Okay, so that's the other positive effect of using faster algorithms that converge faster. You need less computation and you need less communication in general. Okay, then the next algorithm that I introduce is FedProx. And it's based on replacing the gradient step by the proximal operator. So this is related to different characterizations of an optimum. So you can characterize the solution of an optimization problem as also as a fixed point of this proximal operator. So the minima of this loss function Li are exactly the fixed points of this operator that is defined by this argmin. This is another characterization of the optima. Beside zero gradient condition. And it turns out in some settings this proximal operator here, so this corresponds yet to another fixed point operator F, can have even faster convergence than Fed averaging. Okay. Yeah, so in general, this is maybe the most generic algorithm that I introduced today, FedRelax, federated relaxation, which is based on characterizing the solutions of GTVMin via blockwise optima. So any solution of this problem must be such that if you fix all local model parameters at all devices except one, then minimizing over this model parameters of this one device must result in the same model parameter as we used in the solution. That's kind of a self-consistency condition for a solution. Yeah, and in this, with this characterization, you get an operator that is used in this fixed point characterization, and this operator is this argmin here, which you just apply in each iteration. So this is the common theme of all these algorithms. You find an operator calligraphic F that allows a fixed point characterization, and then you just repeatedly apply it. And working out the application of this operator results in this different or seemingly very different algorithms, but they are just different. They are just implementations of different choices for this calligraphic F. Yeah, and this formulation or this formalism is quite generic. So you can write this down. At least you can write it down also for non-parametric models. So why do I torture you with anything else than gradient methods or federated averaging? Because this doesn't work for decision trees. So who of you have seen a federated method or federated decision tree methods? So typically, who of you has heard about federated averaging before this course? Awesome. Okay. Very good. Very good. So you're fresh. You're not biased. But I want to emphasize again that in this formulation, the local models can be anything. So we don't use model parameters. This means that the local models can be decision trees, or they can be deep neural networks of completely different structure. So I use a convolutional neural network, another device uses a transformer network. Or yet a third device uses decision trees, completely non-parametric. So this formulation allows for an almost arbitrary mashup or mix-up of different models. So this is very flexible. Okay, so now to the final part of my lecture today, which is asynchronous federated learning algorithms. So again, the starting point of the design of federated learning algorithms in this course is you formulate GTVMin, you find a fixed point characterization using an operator f, and then you iterate it. So far, so good. But now we give up this strict regime of synchronous updates. So we allow the model parameters to be outdated or stale. We allow for staleness. So we allow in these updates, first of all, we allow the model parameters to be outdated. So the update at node I uses old information at other nodes, and we allow for some nodes to don't do anything. So only a subset of nodes is active in each iteration. And this allows now, this broadens the range or the applicability of these models to much more applications. Applications where some devices are inactive. I mean, this is the standard case. So sometimes I want to collaborate to retrain my personal healthcare assistant. Sometimes I don't because I'm running out of battery, because I don't want it to contribute. So in each iteration, only a subset of nodes is active. And also the nodes that are active that apply this operator, they might use outdated model parameters from other nodes. So I have illustrated this here with a very simple federated learning system that consists of two nodes. And we look at it for the first 4 time steps. So node 1 and these filled circles means that the corresponding node or device is active at this time step. So in the first time step, both nodes, both devices 1 and 2 are active. So they run their local update, whatever it is, a gradient step or a proximal step. And then they move on to the next time step where node 1 is sleeping, running out of battery or having something better to do. And node 2 is active, still does an update. But of course, it cannot do this update with the newest version of node I because there was no communication. So already in this second time step, node I2 must use outdated information from node 1, which I should also include here with an arrow. Yes. Then in time step 3, node 1 wakes up or finds itself now, it would be a good time to do again an iteration, but it didn't get the latest update from node 2. So node 1 must use the outdated model parameter of node 2, which the node 2 computed at time 1. Okay. And now the question is, when does it still work? So how much delay can we tolerate? Can these delays, these arrows become arbitrarily long? So some nodes, they get more and more outdated information from others. So what's the limit? When does it break? And it turns out there are some design choices for these loss functions and discrepancy terms such that the resulting algorithm, so in the end, it depends on this operator f again. It depends on the operator f. So if this operator f or fi, these node-wise fixed point operators, if they are contractions in a useful norm, and I will show you in a second which norm it should be, then the resulting algorithm is totally asynchronous. And this is kind of the most general algorithms. They are the most robust. For example, these totally asynchronous algorithms, they allow for arbitrarily long delays. So these delays between nodes can become arbitrarily long as each node never dies out. So as long as each node once in a while wakes up, does an update, and sends it to others, it will work. The algorithm will work. So this is kind of the most badass algorithms, totally asynchronous federated learning algorithms. They can tolerate the most imperfections. And then there's another class of algorithms which is called partially asynchronous algorithms. They are not so badass, but still quite good. They tolerate a fixed maximum delay. So if you are sure that as long as the maximum delay of your neighbor's information is below 10, let's say, it works. But if the delay gets larger than 10, it breaks. So there's some breaking point for the maximum delay in a partially asynchronous algorithm. Okay, so yeah, I want to also point out that there's this duality between the computers or the hardware that runs an algorithm that is kind of ordered in an opposite way as the algorithms. So a totally asynchronous computer is the most crappy computer because it needs super good algorithms, totally asynchronous algorithms to work. So the more you require from an algorithm, the more elite the computers become. So if you require partially asynchronous algorithms with maximum delay 10, then this is a subset of all the computers that can run algorithms that tolerate a delay up to 100. So this is the reverse ordering as for algorithms. So totally asynchronous algorithms are the absolute elite algorithms. These are the most badass algorithms. So try to always design a totally asynchronous algorithm. And how can you design it? Well, it turns out that one sufficient condition, and I'm actually not quite sure on the spot here if this is also necessary. So this would also be a nice exercise or even a research project. So how close to optimal is this condition in a sense? This condition is the maximum norm or the block maximum norm of these fixed point operators need to be upper bounded by some constant kappa that is strictly smaller than 1. And if you can show that these fixed point operators that are underlying your federated learning algorithm, they are this block maximum norm contraction, then first of all, your algorithm is totally asynchronous. So it is a badass algorithm then. And you can characterize the convergence speed for partial, if it's a partial asynchronous algorithm, or when you run the algorithm in a partially asynchronous mode. And this convergence rate is quite revealing because it basically tells us that you lose convergence speed by a factor that is proportional to the maximum delay. So if you increase the maximum delay by a factor of 2, you must do twice as many iterations, which is quite natural, or at least intuitive. This maximum delay scales the number of iterations you need. When you have maximum delay 10 and you need 100 iterations, then if you have maximum delay 20, you need 200 iterations to achieve the same accuracy or optimization error. Okay, so this, and I've put here the reference. It's a not so old paper from Journal of Machine Learning Research, which worked out this analysis. I mean, this analysis is pretty nice and conceptually not too challenging. So it's based on fixed point iterations. So you want to characterize the contraction rate of an operator, and then use basically the mathematics required to prove Banach's fixed point theorem. I guess you have heard about this in the last lecture. And so the mathematics is not too elaborate, but working out this nice bounds here took some effort, and I'm really grateful to have this paper who wrote this up. And yeah, it's a nice, cute convergence bound, which applies for partially asynchronous algorithms. Okay, yeah, how can we control this kappa? So as I mentioned, all these results apply for contractions in the block maximum norm. How can we ensure that this update operator is a block maximum norm contraction? Well, you need to work out this contraction factor, or you need to show this bound by using the properties of the local loss functions and the discrepancy or disagreement measure. Okay, so and these are design choices to some extent. So by tuning or by shaping the loss functions, the local loss functions, you might ensure that kappa is smaller than 1. And one way to shape the loss function that I told you earlier could be, for example, add a ridge term. So adding this ridge term could make this overall operator a block maximum contraction. What is it? A block maximum norm contraction. Okay. Yeah, that's what I had on my mind today. So again, to reiterate, in this course, we formulate federated learning as, first of all, an optimization problem, so GTV minimization. Then we characterize the solution of GTV minimization as fixed points of some operator. And there are different ways to construct the operator. One way is via the zero gradient condition. Another construction is based on this coordinate or block coordinate wise minimum property or self-consistency property. The resulting operators are different, and hopefully the operator that you end up with is a contraction. And if it's a contraction, in particular, if it's a contraction with respect to the block maximum norm, you obtain a totally asynchronous federated learning algorithm. So I guess that's the ultimate goal. And as mentioned, the properties of this operator F, they are directly tied to the properties, to the shape of the local loss functions, if they are strongly convex, if they are smooth, and so on and so forth. So by choosing this loss function, you shape the contraction properties of this operator F. Okay, so I hope you are now all passionate about fixed point iterations and happy to take your questions. There's one comment on Zoom. Why not back up? So there's a question, why not back up model parameters in different nodes and keep updating them virtually until the main node goes online again? Yeah, I'm not sure if I understand this, because if you have outdated information and you don't get new information, there's not much point to do updates, because you repeatedly do updates with outdated information. It can be that you can make some progress in the local loss function, yes. But in general, I think it will not help too much. Then the next question, does modifying the objective to imposing a certain kappa in order to guarantee some asynchronous properties have negative side effects? Very good point. So as I mentioned, that we can shape these contraction properties F by changing loss functions. But if you change or perturb loss functions by adding a ridge term, you pull the solution away from the original GTVMin problem. So you introduce, could be called a bias. So you might introduce a bias, which might hurt the accuracy of the trained model. So in a sense, you might speed up convergence of the training algorithm, but the algorithm converges to a worse model. Very good question. Yeah. Then there's a question, will we have only coding-based lectures? No. So in this course, we don't have only coding-based lectures. Then next question, does asynchrony allow adding new devices into a network as it is training? Yes. So this model here, in this asynchronous computational model, we can also capture new devices entering the network, continuously entering the network, and also potentially leaving. However, to make convergence statements, this needs to happen regularly. So we need each device to show up infinitely often to make these convergence statements. But then you could, of course, model these new devices who enter also as noise. So if these new devices are only there for a few time steps, then it would be better to not model it as an asynchronous federated learning algorithm over a complete federated learning network, but rather to look at the network without those nodes and consider the impact of these nodes who enter as noise or perturbations. Okay, there's another question. In the asynchronous model, can nodes keep doing local stochastic gradient steps if they can't broadcast their model? Do we know any theory aspect that characterizes the impact of heterogeneous number of local steps on performance? Yeah, very good. I mean, this is in the end, it boils down to how do you construct these update operators, calligraphic F? So should this be 1 gradient step? Should this be 3 gradient steps or 10 gradient steps? And how does this number of gradient steps depend on the maximum delay, for example, or the network structure? Is it what's the average node degree in the network? And these are research questions, so I don't know. These are open, I think open, so I didn't see a comprehensive solution or theory for this, but these are open research questions. And I would invite you, if you want to start such a research project, as a follow-up to this course. Okay, if there are no other questions, then I thank for your attention and see you next Monday in lecture 5 on federated clustering.